Now that we recognize that both myoglobin and hemoglobin have a deoxy and an oxy form, we might begin to ponder what it is that affects whether that's in the oxy form or the deoxy form. And inevitably we come to the conclusion, or hopefully anyway, right, that it has to do with the concentration of oxygen. So the more oxygen is present, the more likely it is that that particular molecule will be oxy in form. So we refer generally to the amount of oxygen present by looking at the partial pressure of oxygen gas. And so we'll measure this in torr, also millimeters of mercury, however you want to express that, they're equivalent. And in the graph that we're about to draw, we recognize that this particular pressure is noted on the x-axis. So the partial pressure of oxygen in torr. Now just to think of a couple of regions or environments where we might see a variety of partial pressures of oxygen, let's just think through that. A partial pressure of 100 in terms of environment, that would be sea level. So at sea level, the partial pressure of oxygen is right at that highest level. And so coming on down from there, now Laramie is much lower than that, somewhere around 70. And if you keep on coming down, you might think of environments where that continues to be true. For example, at the level of your tissues, the partial pressure of oxygen at that level is around 40. So what we see is a changing environment then is going to affect whether or not the myoglobin and hemoglobin are in their oxygenated forms or in their deoxygenated forms. Now that's what we're going to see as being a function of partial pressure on the y-axis. So here we're looking at fractional saturation. That is, what percentage of the molecules of myoglobin and hemoglobin are bound to oxygen. Now we might go ahead and express that in terms of an equation just so we are all thinking along the same lines. Fractional saturation is basically just the concentration of myoglobin that's oxygenated divided by the total concentration of myoglobin, which be the oxygenated and the deoxygenated. Now the same thing could be expressed for the fractional saturation of hemoglobin. We could just put that in parentheses, I guess, if you will, and express the same exact thing for hemoglobin. Fractional saturation has the same meaning for both molecules. That is, what fraction of the molecule is bound to oxygen. So that's what we're going to be seeing on the y-axis. What percentage or what fraction are bound to oxygen at certain given partial pressures of oxygen. Now I've gone ahead and made a couple of marks on the graph to help me in drawing the curves for saturation for both molecules. We're going to go ahead and draw myoglobin in red and then hemoglobin in blue. No particular indication of their oxygenation state, right, with those colors, because we know that the oxidation state of the iron determines those colors. No, I didn't intend anything there. That's funny. Okay, so if we can, we're going to go ahead and draw the oxygen binding curve for myoglobin. It's going to come up here through its 50% saturation point, continue to start to curve. It's a hyperbolic curve. It's going to then asymptotically approach 100% saturation. So what we notice then is that the oxygen binding curve for myoglobin is what we term hyperbolic. If I can spell, hyperbolic. Okay. What that means is that there is one equilibrium constant. We know that because we recognize that there's only one heme porphyrin and one oxygen binding site. So there's one KEQ, and that describes the binding of one oxygen molecule. So we see that hyperbolic binding curve. Now hemoglobin is going to be great deal different than myoglobin, because remember that it has 4 oxygen binding sites at each one of the pyrrole rings, at each one of the central iron ions in each of the 4 subunits of hemoglobin. So the binding curve of hemoglobin much more sigmoidal in nature. You can see it almost having a bit of an S shape to it. So this is representing the fact that it is described by multiple and cooperative binding of oxygen. That is, there is more than one oxygen molecule that can bind. We remember there are 4, right? And so what happens is that this sigmoidal curve actually represents the fact that with each oxygen that binds to hemoglobin, it becomes increasingly more favorable for the next oxygen molecules to bind. So we have a sigmoidal curve rather than a hyperbolic. And oxygen binding is cooperative. That means that as one oxygen molecule binds, it makes it more likely, more favorable for the next oxygen to bind, and so on down. This is called positive cooperativity for binding. Hey, so notice how we're finding out that the structure of hemoglobin really is determining its function. The fact that it has multiple subunits is allowing it to display a sigmoidal rather than a hyperbolic binding curve. So we see then that this is definitely affecting its structure. Now there's an important point on these curves that is often talked about. This is the point at which the molecules are 50% saturated. So if we draw a bit of a dotted line out here to what we call the P50. The P50 describes the point at which the fractional saturation is at 50%. So we notice that these are very, very different for myoglobin and hemoglobin. If you just continue the line on down for myoglobin, we notice that this occurs 50% saturation for myoglobin occurs at a very low partial pressure. In fact, it's a partial pressure of 2.8. So at only 2.8 torr, myoglobin is 50% saturated. Now look at how different that is for hemoglobin. At its P50, at its fractional saturation 50%, the pressure there is 26. So the P50 then for hemoglobin is 26 torr. Wow, there has to be a much, much higher concentration of oxygen, or a much higher partial pressure of oxygen for hemoglobin to be 50% saturated. Now, this is going to have very important consequences in terms of the transfer of oxygen from hemoglobin to myoglobin. But one thing that we could state before we leave this behind is that if you look at the two curves, the sigmoidal hemoglobin curve and the hyperbolic myoglobin curve, one thing that you notice is that at all partial pressures, myoglobin has a greater fractional saturation. So what that means then is that myoglobin has a greater affinity for oxygen at all partial pressures.
We can derive an equation for the myoglobin-oxygen binding curve. And in order to begin, let's write the dissociation equation, equilibrium equation for the dissociation of myoglobin and oxygen. And we can write the dissociation constant for this. Additionally, we had that trusty equation for fractional saturation of myoglobin. We had expressed it as the concentration of oxy-myoglobin divided by the total concentration of myoglobin, so deoxy plus oxy. And what we can do here is actually solve for the concentration of myoglobin in its oxy form here in the dissociation constant equation and end up with we can then take this entire conglomerate and plug it in for the concentration of myoglobin oxygen in the fractional saturation equation. It begins to look a little bit messy, but we're going to be able to simplify. And what we can do now is actually pull out the myoglobin over K terms, which then leads to a simplification of this equation that looks a lot less cumbersome. So concentration of oxygen over K plus concentration of oxygen. So then this is a good-looking equation, but we will go ahead and recall that concentration of oxygen, because oxygen is a gas, it can be really conveniently, in this case, expressed as partial pressure. That's what we've been thinking about. So we can just plug in to this equation for partial pressure of O2 over K plus partial pressure of O2. And now we get to note something really important that we're going to talk again and again and again about K, is its definition. So if we remember back to this curve, forgive the chicken scratch, but what we can recall, if we've got fractional saturation on the Y and partial pressure of oxygen on the X, and we've got our rectangular hyperbola here. So what we note is that K is defined as the partial pressure of oxygen at which the fractional saturation is 50%. So that's actually the definition of K. So we also recognize that, of course, that's P50, right? Because that is the fractional saturation at 50%, or the 50% fractional saturation that occurs at that location. So we can nicely substitute in. So now we have a really useful equation. We can think about a situation. Maybe we want to know what is a fractional saturation of myoglobin when the partial pressure is 5 torr. We can go ahead and calculate that. So we'll say it's 5 torr over, we know P50 is 2.8, of course. Plus 5 torr. So fractional saturation is equal to, what's 64%. Now we could go qualitatively check this and look on our curve and see, does that check out? Does it look like at about 5 torr that myoglobin is about 64% saturated? And it certainly does, but go take a look at that curve.